I want to begin our discussion of protein purification methods by reminding us about protein chemistry and side chain chemistry. We'll see that much of protein purification, much of the details of protein purification have to do with understanding variations in side chain chemistry, such as overall charge of a protein, overall hydrophobicity of a protein, etc. So let's just look back again at this hydropathy scale that we discussed in the previous lecture. And we see here on top that we have a hydropathy plot for a rhodopsin, which is a membrane-bound protein, you will remember. And you see this periodicity as hydrophobicity goes down and then up and then down and then up again, that we have a regular transmembrane structure. Whereas if we look at myoglobin, we see that it's wandering back and forth, but nothing nearly so strong as this for the soluble molecule as we see for the membrane-bound protein. I'll point out as well that here's the sort of so-called Kite and Doolittle scale published back in 1982. This is still a commonly used hydrophobicity scale, but I'll point out to you that tryptophan doesn't appear to be the most hydrophobic molecule. This isn't a free energy, by the way. This is just a relative hydrophilicity or hydrophobicity. It looks like other amino acids are much more hydrophobic than say tryptophan, which according to our water octanol scale was the most hydrophobic of the side chains. So again, pointing out that ambiguity to you, and that who's the most hydrophobic depends on what kind of parameters we're really considering. So protein side chain chemistry, critically important to understanding how we purify proteins. I just wanted to give you a quick overview of some of the basic methods of protein purification, starting with reverse phase chromatography. Reverse phase chromatography is as opposed to normal phase chromatography, or aqueous phase chromatography. And the trick here is that we alter the hydrophobicity or the polarity of the solvent or the mobile phase that's used in the chromatography itself. Typically, you'll see reverse phase chromatography used in the HPLC context, that is high performance liquid chromatography. The trick here is to make use of the hydrophobic effect. So we have a bead. Here's the matrix bead covered with in this case probably a 10 carbon aliphatic chain, so a non-polar matrix, and then we adhere the protein by flowing it over the aqueous matrix so that the protein, which might have a hydrophobic patch, prefers to interact with the column matrix more than it prefers to interact with water molecules. So again, ordered water molecules around both the nonpolar matrix and the nonpolar patches on the protein. And then as we replace the aqueous solvent with an organic phase, for example acetonitrile, then we eventually displace the protein based on this diminution of the protein's affinity for the column matrix. So as the mobile phase becomes more nonpolar, the protein can then pop off of the matrix and flow out. And of course, like all purification techniques, we're relying on a variation perhaps in the relative affinity of any given protein for the matrix, so that if there are several proteins stuck to the matrix, one will elute at a different concentration of organic phase than another, thereby achieving a separation. The reverse phase chromatography is less relevant to us in our biochemistry laboratory. We won't be doing any HPLC in the lab. Instead, we'll be relying on some forms of affinity chromatography, and I'm going to place ion exchange chromatography firmly in the category of affinity chromatography, and I'll explain why in a moment. Here again, I have a cross-section of a bead, except for in this case, instead of being covered with a nonpolar matrix, where the bead is decorated with charges. In this case, a positively charged functionalization of the bead. The bead themselves are some carbohydrate polymer that's fairly non-reactive. So here's the cartoon of a column packed with these positively charged beads. So we would say that this is an anion exchange column. That is to say, anions will bind to the column matrix because they're negatively charged, and then we can alter the affinity of the protein for the matrix by changing a variety of things, and most importantly by changing the ionic strength of the solution. So let's go over that again. We have a positively charged matrix. We introduce to that matrix our protein, and if our protein is negatively charged or oppositely charged from the bead, in this case again anion exchange, then it will adhere to the resin, to the column matrix, until we affect the relative affinity. And let's say that we change the relative affinity of the protein for the matrix by altering the ionic strength. We can do that by altering the salt concentration, for example, of the mobile phase. So at low salt concentration, a negatively charged protein will adhere to this matrix, and as we increase the salt concentration, that is the chloride concentration, that is the negative charge available, then the protein will become displaced as the chloride ions outcompete with the protein for position on the matrix. And then, of course, the protein will flow through the column, and we'll collect that as a fraction. There's other ways that we can affect the affinity of the protein for ion exchange chromatography, or for the charged matrix. By changing the pH, we can affect the charge state of the protein, and thereby, and this is something that we'll discuss in class, but obviously when we change the pH, we alter the charge state of all of the ionizable side chains, and then we affect the overall charge on the protein, and this in turn affects the affinity of the protein for the positively charged bead. I should also point out that one can perform cation exchange chromatography by replacing the positively charged matrix with a negatively charged matrix. So very flexible. But I mentioned at the beginning that I would place ion exchange chromatography in the category of affinity chromatography, and in this case we're considering that there's an affinity of the protein for the matrix, and that affinity in this case happens to simply be the charge state of the molecule, the relative charge on the molecule. There are other versions of affinity chromatography. Metal ion chelation is another important one, and we will discuss this a little bit in class and a little bit in laboratory. But essentially, in metal ion chelation, instead of having a positively charged bead, what we do is affix a nickel ion to functional groups on the surface of the bead, and the nickel ions interact very tightly with histidine side chains. So if the histidines are positioned appropriately in the chain, frequently they're added through some simple genetic engineering as an N-terminal or C-terminal tail of the protein. Then those proteins will adhere to a nickel matrix, and then we can elute that protein, of course, by adding as a co-solute imidazole, which is, of course, what histidine side chain is. So metal ion chelation, ligand binding interactions. We haven't talked a lot about ligand binding interactions, but of course many proteins bind small molecules, and they even bind other proteins. But focusing on small molecules for a moment, you will perform this kind of chromatography in lab. What we'll do is functionalize the bead with the actual molecule that the protein binds, that the protein has an affinity for, and then we use that as our column matrix, so that when we flow our protein over the matrix, those proteins that have an affinity for the molecule that's now modifying the surface of the bead, those proteins will adhere to the matrix, and other proteins that don't bind those molecules will flow through. So again, we would elute those bound proteins by presenting the column with an excess of the free ligand, and that of course the protein, that ligand will bind to the protein, and the protein will be released from the matrix and it will flow through. And again, reminding you that there's two kinds of separation that take place here. First of all, there's proteins that don't have any affinity for the matrix. Those flow through, leaving behind those proteins which do. But then we rely perhaps on the fact that different proteins bound to the matrix have slightly different affinities, and therefore we can release them from the protein by presenting the matrix. We can release the protein from the matrix by presenting the matrix with a different solute composition. We also can use protein-protein interactions to purify other proteins. In this case, we'd functionalize the bead not with a small molecule, but with a protein for which our target molecule that we're purifying has some affinity. So, affinity chromatography, in my definition, I'm simply categorizing any kinds of interaction between protein and the bead that have to do with some binding event, whether it's a charge-charge interaction, or more small molecule ligand interactions, or even protein-protein interactions. Another important one that I can't avoid discussing is size exclusion chromatography. This is another method that we will use in the laboratory this semester, more properly called gel permeation chromatography or gel filtration. In this case, we separate based on molecular size, and it's a very simple idea. We design a gel matrix, or a column matrix here represented with blue, that has some pore size, and we can dial in the size of the pore. And in this, on the left here, we see a hypothetical column with blue beads with a particular pore size, and size exclusion gives you the whole idea. If the molecules that were flowing over the column are too big to enter the pore, then they flow through very, very rapidly. Whereas if there are molecules that are small and that may enter the pore, then they enter the pore and they're retarded as they flow through the column and then only elute very, very slowly. So again, large particles can't enter and are excluded, and small particles can enter, and then they are slowed down as they flow through the column. So when we look at a chromatogram, right, and a chromatogram is simply a function of some metric of the presence or absence of the protein. How about ultraviolet absorbance of tryptophan amino acids? And then on the x-axis here we have time. So we begin flowing, and we see that the large particles elute quickly, and the small particles elute slowly. So this is frequently used for to desalt proteins. So in this case, we might not be separating a protein from another protein, but we might be separating a protein from, say, sodium chloride or some other buffer component. The buffer might stay behind on the column as the protein flows through quickly. And by the time the salt or whatever the solute is we're trying to remove comes off the column, our protein has already run through. So, gel permeation or gel filtration chromatography. We use this in the laboratory as a means of cleaning up our protein. It's also very useful as a protein separations method, but we will probably not use that so much in our laboratory. Before moving away from this simple overview of some basic chromatographic methods for protein purification, I just wanted to show you a typical setup of a protein purification device. Very straightforward. Beginning with buffer reservoirs, which allow us to alter the solution conditions on the column, and then here's a manifold that might allow us to run that column elute perhaps through different columns or through different pumps, or to allow us to treat the protein and buffers flowing through the column in a variety of different ways. There are pumps that are drawing the liquid through the column. And then, of course, there's some detection method. And a UV detector is a standard method. There are plenty of other detection methods that we won't go into today, but suffice it to say that if your protein has a tryptophan, then you have a handle for monitoring the presence or absence of your protein, or the location of your protein on your column. Of course, as the protein flows through the column, we can use a fraction collector to collect the protein as it flows through. So the key here being that we separate out the components that flow through the column and that elute from the column. All right. Finally, I want to describe electrophoresis, which while we won't use it as a purification method, it may be used as a purification method. Instead, it's a standard method diagnostic tool for determining purity of our protein, and this is the way that we'll use electrophoresis in our biochemistry laboratory. So I want to just describe the background of electrophoresis to you in very simple terms, and then show you what an electrophoresis gel, so we use a polyacrylamide gel matrix for our electrophoresis, show you what that gel might look like. First of all, we can say that anytime we have a electric charge and an applied field of some strength, the charged particle, feels a force. That can be written as a velocity, and here we'll say that if we assume that there's a spherical particle and there's some viscosity in the matrix through which the particle is flowing, then we can write down a velocity. And the velocity seems to depend on the charge, the electric field, the shape, and the viscosity, as well as the size, A. Very important. That's going to pop up later. But it turns out that in terms of describing proteins moving through matrices, this is a very inadequate description. Mostly because, well, a couple of reasons. Because it's a little bit more complicated to describe the actual average charge of the molecule than simply by tallying up the charges, as we tend to do in a biochemistry class. So this requires a much more formal treatment to get it precise and actually correct. The other problem is that the matrices that we tend to use for electrophoresis are very complicated matrices. And as I mentioned, polyacrylamide gel electrophoresis is standard for proteins, but it might be a fibrous matrix, could be paper. We don't really know. But in any case, a whole complex set of parameters that we'd have to account for to really understand the velocity of the particle in an electrophoresis experiment. However, let's just accept that we can add those parameters and account for them empirically, which we'll describe in just a moment. Suffice it to say for now that we can think of a protein's mobility, right, or the particle's mobility, if we just divide this velocity by the magnitude of that electric field. And we see here when mu, or mobility, the electric field drops out, and we still have our charge parameter, we still have our shape parameter, we still have our viscosity parameter, and we still have our size parameter. And then we have added something new here, kappa. So this is an empirical fudge factor, and we'll call it a screening or matrix fudge factor because it accounts for the fact that in an actual polyacrylamide electrophoresis of a protein, the charge on the molecules is not what's driving their actual separation. And let me back up and say that in an electrophoresis experiment, as we'll see in just a moment, it's the separation of proteins from one another that we want to accomplish to determine, for example, the relative purity of a protein in a particular sample. So it's not enough to say that we'll separate based on charge. We ultimately want to be separating based on size. And we see that if we perform our experiment, which we always do, in the presence of a large concentration of counterions, then effectively the charge to mass ratio of all of the molecules is the same, and all of this stuff falls away when we apply kappa, our screening factor, so that we see that the mobility reduces to something like 1 over A, or 1 over the size. And actually that should be the maybe the log of 1 over A, which you will see in the lab. So what does that look like? Well, here's a snapshot of a polyacrylamide gel, and this has been stained with some dye that binds to all proteins. And typically what you'll see is a molecular weight standard, and then these are different samples. Doesn't matter for our purposes what they are. And what we see is that the heavier proteins stay at the top of the gel, lighter proteins run down, right? Mobility goes as the inverse of the size, yeah? And if you plot what these molecular weight standards actually are, which I believe you'll get to do in the lab, you'll see that actually they separate based on the log of that, log dependence of that size. Now, I mentioned that it's possible to do purifications by electrophoresis, obviously, but in practice it's not very useful for purifying large quantities. There is a method that I'm not going to discuss called capillary electrophoresis, where the electric field is applied not over a gel of some kind, whether a covalent matrix like polyacrylamide or non-covalent matrix like agarose. Instead, it's applied through a very narrow capillary, but again, achieving the separation in part based on the charge of the molecules involved. Okay, with that we come to the end of series 2. Our next video, set of videos, will be on molecular structure representations and molecular structure determination techniques. See you there.